In this video, we're going to talk about energy and the ways that energy is transferred from one place to another in chemistry. Thermochemistry is the branch of chemistry that deals with how energy is related to chemical reactions and changes of state. In order for chemical reactions to happen, bonds must be broken and new bonds must be formed. And these processes require the transfer of energy. Physical changes, such as phase changes from solid to liquid and liquid to gas, etc., also involve the transfer of energy. Energy is needed to overcome intermolecular forces, for example. From past courses like physics and physical science, you may already be aware that energy is the capacity to do work or to produce heat. There are two main types of energy. The first is potential energy, and this is energy an object has because of its relative position or composition or condition. Gravitational potential energy is one kind of potential energy. The potential energy that's stored in a ball that's been raised over the ground depends on whether it's closer to the earth or farther from it. The potential energy in a spring is going to change depending on whether the spring is stretched or compressed. In chemistry, we're concerned with electric or coulombic potential energy, which occurs between charged particles. Remember this curve? Most atoms have lower or more negative potential energy when they're bonded together. The electrons of one are attracted to the nucleus of the other, and vice versa. Likewise, oppositely charged particles have lower potential energy when they're held together by electrostatic attractions, such as ionic bonds or intermolecular forces. And there's a typical distance that is optimal for each pair of atoms, or for each ion, or for each polar molecule, etc. Kinetic energy is the energy an object possesses because of its motion. The amount of kinetic energy an object or particle has is directly proportional to its mass and the square of its velocity. You will see this equation, Ke equals 1/2 mv squared. And you have seen this before. When we're talking about tiny particles like molecules and atoms and ions, we typically see kinetic energy in the form of translation, which is the movement of particles from one place to another. We also see kinetic energy in the rotation of molecules, and also in the vibration of particles, like the vibrations that compress and stretch the bonds in molecules. Now I want to talk about something that isn't strictly part of the AP curriculum, but it's in your textbook, and it's something I think is useful to know, and I think it's something that's going to help understand all of the stuff we're going to talk about in this unit. If you were to add up all these different kinds of kinetic and potential energies, you get something called internal energy. And sometimes this is represented with a U and sometimes with a capital E. And you can think of internal energy as all the different types of energy that occur within a substance that are all added together. In this unit, we are concerned about the changes that can happen in internal energy, or the total energy of a system. And there are two main things that can cause these energy changes. The first one is heat. The second one involves work that is done on a system or by a system. And we'll talk about what all of this means in just a minute. Before we can go any farther, we need to define what a system is. A system is the set of substances and energy being studied. Often this is a chemical reaction where bonds are broken and formed inside the system. The system can also be molecules that are undergoing phase change, where the intermolecular attractions are being formed or overcome. The stuff that's outside the system is called the surroundings. It's anything that is not reacting or rearranging. It can be the beaker itself, or the test tube, or the room, or a solution that the chemical reaction is occurring in, or that a substance is dissolving into. It can be your temperature probe, or thermometer, or the stirring bar. It can even be your hands feeling the heat in the test tube, or in the beaker, or having the heat sucked out of them. The universe is the system plus the surroundings. It's everything. Now, the reason we care about system, surroundings, and universe is because the energy changes that occur during a chemical reaction or physical change, like a phase change, typically involve the transfer of energy between the system and its surroundings. When energy is transferred from the surroundings into the system, we call this process endothermic. We say that the system takes in energy, or energy enters the system. Endothermic, enter. When energy from the system is released to the surroundings, we call this exothermic. Energy exits the system. The system gives off energy to the surroundings. As I said before, there are two main ways to change the internal energy of a system. The first one is to add or take away heat, and the second one involves work that's done on the system or by the system. Now let's talk about these two things. We're going to start with heat. In order to do this, we're going to have to define a couple things. Thermal energy is the energy within a system that is due to the movement of the particles within that system. It's the total kinetic energy that the system possesses, and we can measure this energy using temperature. Temperature is a measure of the average kinetic energy of the particles in a system, and we've talked about this in previous units. Heat is the transfer of thermal energy from one body to another because of difference in temperature. Heat measures how energy moves or flows. It's not the same thing as temperature, but it can result in a temperature change. Heat is also not the same thing as thermal energy, it's the transfer of it. We often talk about heat moving from the system to the surroundings, and that would be an exothermic process, or from the surroundings to the system, and that would be an endothermic process. Heat is measured in joules, and it is represented by the letter Q. Now, one thing that's important to remember is that when we think about energy changes, we always think about them from the perspective of the system, from the perspective of the chemical reaction or the physical change that's occurring. It's important to remember this when we talk about the sign of a change in an equation. If heat goes into the system, Q is positive, and this is an endothermic process because heat is entering, and the system is gaining heat. If heat leaves a system, Q is negative. This is an exothermic process because heat is exiting the system. The system is losing heat. To sum up, heat is one way we can change the internal energy of a system. The other thing that can cause the internal energy of a system to change is through work done on the system or by the system. This is a little more difficult to understand, but stay with me here. In physical science, you may have learned that work equals force times distance. You might ask, how does work happen in chemistry since we're obviously not pushing boxes around? Well, in chemistry, there are two types of work that we commonly think about. One of these is electrochemical work, and this is the kind of work related to the flow of electrical current and electric potential. You'll study this kind of work in physics. The other type of work we talk about is pressure volume work, and this is related to the compression and expansion of gases. If you have a chemical reaction that produces a gas, for example, the gas will often push the surroundings as it expands. In other words, it may push against the air that's surrounding it. When it does this, it does work, and sometimes we call this pressure volume work. One of the easiest ways to visualize pressure volume work is by thinking of a piston. The gas is inside the piston, we call this the system, and everything else is the surroundings. If we push down on the piston, we exert a force on the piston and the piston moves a certain distance. Now the volume decreases. We say that we are doing work on the gas, which means energy is going into the system. We say that work is being done on the system, on the gas, by the surroundings, which is us pushing on it. When this happens, the average kinetic energy of the particles in the system increases, and the temperature increases too. Remember PV equals nRT? Pressure goes up, temperature goes up. The gas has gained energy. Compressing a gas is therefore an endothermic process because energy is entering the system, in this case, the gas. If the gas inside a piston expands enough to push the piston up against the air that surrounds it, we say that the system does work on the surroundings. Work is being done by the system or by the gas in the cylinder, and energy is going out of the system, out of the gas. The average kinetic energy of the particles in the gas decreases and the temperature goes down, and we can also intuit this from the ideal gas law. That's why expanding gases get cooler. Energy is given off. The process is exothermic because energy is exiting the gas. So to recap, there are two main ways to change the internal energy of a system. The first one is to add or take away heat, and the second one is to do work on the system or have the system do work. This equation sums this up where delta E equals the change in internal energy. You could also have a U there. And Q is heat and W is work. Now, you won't be tested on this, but I think it is helpful because you can see how changes in heat and work can relate to the energy of the system. There are a couple of observations that can suggest to us that energy changes are occurring. And the first of these is a change in temperature. And the second is a change in the volume of the gas. This should now make a little sense to you because of what you know about internal energy, heat, and work. In the next video, we'll talk a little more about exothermic and endothermic processes.